Welcome to Automated Flight Week 6 Control Theory, where we will look at different block diagrams and see how we can simplify them. So there will be four basic rules. The one where we look at superposition, where we have a block diagram with multiple inputs. If we have a serial system, parallel systems, feedback systems, and we'll then look at a way of moving a summing point if that would help us simplify the block diagram. And finally, we will look at an example. So if we have multiple inputs and we want to determine what the output is going to be, we do a number of things. One, we set all inputs to 0 except for 1. We calculate the output in that case, and then we go through all the inputs. So we select all the others to 0 and take another one. And once we've done that for all inputs, we add the results together and we are left. We have the resulting formula for our output. Well, let's see how that goes in practice. Here I have U1 and U2 as two inputs, and the second input could be a disturbance, could be anything really, and we have our output. We have one single system, G, and let's start, where we will first take U1 and we will put U2 equal to 0. So in the first case, U2 is 0 and we have our Y is G times U. If we now set the other one to 0, so U1 is equal to 0, we have that Y is, that was U1, U2, and so now to get the complete result, we add these two together, and Y is U2 plus G times U1. And of course, the multiplications are all in the Laplace domain. If we have serial systems, the equivalent system for determining the output, if we have our U, is simply the multiplication of these two systems. So we can reduce these two blocks into a single block where we multiply the two transfer functions in the Laplace domain. If we have parallel systems, we have an addition of the two systems, so G1 plus G2 to get our output. If we have a feedback system with unity feedback, and with unity feedback I mean that there is no factor or transfer function here, we can write it out, but there's a trick to this where we first determine this difference here and we call it E, which will be our error function, and what we get then is that Y, or if I want to write it properly, Y of S, as we are dealing with the Laplace domain, is G of S times E of S, and E of S, our error term, is simply the difference between our input and our output. So this is U of S minus Y of S, and we take this error, we plug it in there, and we find that, and I'll drop the parentheses S, Y is G times U minus Y. Now this is an equation we can solve. That term G times minus Y goes to the other side, and I have 1 plus G times Y is G times U, and I have the total transfer function. So the transfer function is the output over the input is G over 1 plus G. And in the same way, if we have a system here where we don't have just simply unity feedback, but we also have a controller, well, we can take the rule here that we first multiply these two with each other, so we get C and G, and the transfer function here will be CG over 1 plus C times G. And so depending on where we have our controller, it could also be here, but we then get a slightly adapted result. Here we have unity feedback. We get that this, and I'm running out of space here, is G over 1 plus G. And that's our output. And here if we have a controller, we end up with a block diagram like this. So these are the 4 rules where we with which we can simplify our Bollock system. Now there's an extra one where we can move a summing point. And for that I'll just erase this result. That'll be sufficient. So if I take, well, let's take green. If we take a look at the signals that end up here, we have G1 times U minus H times Y. But what if I wanted to move this point to a summing point here? Now I couldn't use the same block diagram because that would mean I wouldn't have just G times U here, but I would have minus H times Y, G times H times Y. And here I only have H times Y. So I have to adapt my block diagram. And what we do is, because we moved this to the left of G1, we now get H divided by G1, and let's see what we're left with. In the previous version we were left with this, and what we have now is that we still have our G1 times U, but now we have G1, well, plus G1 times H over G1 times Y. But you see that the G1 here and the G1 there cancels out, and we're left with G1U, I forgot a minus there, minus H times Y. So it's now an equivalent system, but I have moved my summing point. And I'll just clear the board, and I'd like to show you an example where we use all these techniques. And I'll quickly get rid of this. And so there'll be an example, but there will also be a challenge for you at the end to do it slightly differently. So what I have is, let's say I have an input, a summing point. I have G1 here, another summing point, so these will be pluses. I have a system G2 that goes into system G3, and finally I have my output, but I have 2 feedback loops. One which starts there, and we have H2 here, and that sums over here, and we cut off a branch here, and we have another form of feedback which we'll call H1 that sums over here. So previously we could solve loops or simplify loops, but now we have 2 loops that loop within each other, which make it more complicated. So what I want to do is move this summing point over here, and I will do that. We just saw how we could do that simply by dividing by the transfer function that we are summing over. So we're moving to the left of G1. So if we then remove this here, we have our H2 over G1. So this is the modification, and we can now sum that over here, or into a different point. Maybe for clarity's sake, I will just simply rewrite it slightly differently so that the loops don't become too convoluted. I will just simply add a summing point where I have my u there. And this will add here. So I've moved it out of the way. Well, here, this summing point doesn't do anything anymore. So we can replace that with a solid line, and we have two serial systems. Well, to combine two serial systems, we can simply multiply these with each other. So this doesn't become this becomes a single block with G1, G2. Now, because the loops aren't intertwined anymore, this bit G1 and that H1 form a nice little feedback loop. This is wasn't one of the cases we showed, but we can figure it out in the same way. And this now becomes a block G1, G2 over 1 plus G1, G2 times H1. And I'll leave it up to you as an exercise that if you have a system like this, that the equivalent transfer function is g over 1 plus gh, like this. But I'll leave that up to you to check. We will continue with our example where I will just copy it. And we here have h2 over g1, which now ties into our summing point here. Now we again have two cascaded systems, two cascaded systems. They're in serial, and we can modify that by simply adding G3 there. And now we're left with a loop of which the mathematics are, well, slightly annoying. There is another way by, and this is, I'll leave to you to see if you could have moved that point there where this block and this block become parallel systems, and you can do this with slightly less involved mathematics, but we can simplify this one as well, where we use this formula where we get our transfer function. This is our transfer function. Here we just have a g, and here we have this, so let's copy this. G1, G2, G3 over 1 plus G1, G2, H1 over 1 plus our original transfer function times h, which in our case is h2 over g1. So this does become a bit big, so it is 1 plus g1, g2, g3 over 1 plus g1, g2, h1 times h2 over g1. Now, of course, I don't like a fraction of fractions, so we're going to make this slightly nicer. And I'll just give myself a little space. I want to turn this into a single fraction with this denominator. So I will just skip the diagram for now. This will be G1, G2, G3 over 1 plus G1, G2, H1. So that's simply copying the denominator. And now this 1 will turn into 1 plus G1, G2, H1 plus G1, G2, G3 times H2 over G1, all with the same denominator, 1 plus G1, G2, H1. So now we have two fractions divided by each other. If you have a fraction divided by another fraction, it's the same as multiplying with the inverse of that fraction And if you write that down, you see that this cancels out against this, and we're left with G1, G2, G3 over what we're left with here, 1 plus G1, G2, H1 plus, well, here I have a G1 term which I can cancel out with that one, G2, G3, H2. And this is now the equivalent transfer function of this whole block. So I'll write it down. So this is equivalent with G1, G2, G3 over 1 plus G1, G2, H1 plus G2, G3, H2. And we've taken a rather complicated transfer function where we have multiple interlaced loops and turn it into a single transfer function. And why would we want to do this? Well, if we want to see if it is stable or not, we will be looking at the zeros of the denominator of our transfer function. So we can only look at stability if we can write it as a single transfer function. So as a single input G of a single system G of S. And now we have, well, it's a rather complicated system, but at least now we can look at stability properties. So this is a video where we have taken a block diagram and looked at 4 different main rules of simplifying the block diagram, and added one where we can move a summing point where we can again use these 4 rules to go from complex systems into complex blocks into a single block.